Okay, these are the 13.1, 13.2 notes for Stat Honors. Today, we're going to be talking about the chi-square distribution. So just like the F distribution, the chi-square distribution is a right-skewed curve. So we're right back into the concept of we only have a right tail area. In terms of chi-square, the name, we use the Greek letter chi with a square on it in order to symbolize it, but realize this doesn't mean anything mathematical at all. So don't overlook that or overthink that at all. It's just the symbolism we use for chi-square. That's it. Okay, so we also are going to have degrees of freedom for our chi-square curves. So there'll be a bunch of you'll see there's similarities and differences between each respective curve as we go. So just to be clear, with chi-square, the total area under the curve is again going to be 1, just like all the other curves. Similar to F, the chi-square curve starts at 0. So here's a picture over here. It starts at 0, and then it goes on indefinitely in the right direction. We know it's right-skewed, and basically, as the degrees of freedom becomes larger, so you can see here, here, and here, it becomes less skewed and more normal. But again, this is very similar to F distributions that you've seen before. So just remember that as the chi-square curve increases in sample size and degrees of freedom, it approaches normality. Okay, so chi-square has its own table associated, just like with all the other distributions. If you recall, we had our F curve was S of alpha, and there were two different types, DFN and DFD, degrees of freedom. Well, for this, we're back to only one type of degrees of freedom, so now we're at chi-squared sub alpha and one unique value for degrees of freedom. So what's a good example? So let's say we were looking for chi-squared sub 0.025 at DF is 12. So what does that look like? You're looking for the value of chi-squared that marks the right tail area of 0.025 at degrees of freedom 12. So we would go to our curve. Curve works a lot like the T distribution curve because there's only one DF. So you're looking for 12 degrees of freedom and you're looking for the proper subscript of alpha. So you make your way in to find the 23.37 as our chi-square critical value. So in this scenario, basically this would be the marker between rejection and non-rejection. But just generally, this is what the chi-square distribution looks like. We're not going to go into too much more detail just because you've seen much of this before. We just want to concentrate on getting into the type of tests that you're going to be running. As I said several sections ago when I talked about how we were going to be starting tests that are quite oddball in nature and different, well, we started with ANOVA, we went to regression, both very different oddball, and then we pretty much finished with one of the most oddball ones called the chi-square goodness of fit test. Okay, so what does a goodness of fit test actually compare? The whole point of it is to basically compare some current distribution with some past or theoretical distribution. So I'm going to just go down here for an example so you understand what that means. So let's say, for example, suppose it was widely known via Mars Inc. that the distribution of colors in plain M&Ms is as follows. So something you can definitely relate to. So M&M colors. So suppose Mars releases like a claim that these are the percentages distribution of the colors in M&Ms. So it would be pretty neat to be able to do your own experiment. Take all the M&Ms out, eat them of course while you're counting, but take them all out, and then compare the percentages of colors that you got with our distribution or claim. Well, if you can picture that in your head, which I'm sure you can, then that is an example of a goodness of fit test, which means we're dealing with multiple categories of colors and all types of things, but what it does is it creates a very unique scenario in which to run a test. Okay, so let's take a look at the goodness of fit test itself. We will deal with assumptions at the end because it's really hard to explain the assumptions other than the common simple random sample. Other than that, you're not really going to know what I'm talking about. So I cover that at the end of this example, so we'll get to that later. But let's start with the known alternatives. So the known alternative hypotheses are respectively going to be your null in words, not in symbols, but in words, you're basically going to state that your current distribution is the same as your theoretical distribution. So remember, this is always a statement of equality, so nothing has changed, right? So basically, this distribution is the same as the previous one, whereas the alternative is going to say that they are different. So you'll see when we do that in words in a couple seconds in our M&M's example what that will look like. We always have an alpha for comparison, that's important, but the test statistic is going to be like something that you haven't seen before. So your chi-square test statistic is going to be the sum of these variables are O minus E squared over E. Now it's the sum of the whole thing, by the way. But you don't know what O and E are, so just be clear. So O stands for observed counts. E stands for expected counts. We could also say frequencies, same word, synonyms, but O observed, E expected. So observed is going to be your current distribution, what you actually found to be the case, and your expected is going to be what your theoretical or past distributions frequencies took. That is the key. And we're going to use those in order to determine our chi-square test statistic. Okay, so let's look at our M&M's example. Again, where are we at? So these are the colors right here with the percentages that are claimed by Mars Inc., the company that makes M&M's. So suppose you currently have a large bag of M&M's that contains 632 chocolate candies. I wish I had that right now. That would be quite wonderful. And your goal is to determine if that distribution of colors is accurate. We would logically test this hypothesis at 5% significance level. So here are your hypotheses. It says the bag of M&Ms has the same colored distribution as Mars Inc.'s claim. So what is it saying? It's saying our current distribution is the same as the theoretical distribution, whereas the alternative is going to say that they are different. So your words are going to be very similar. It's just one's going to be the same and one's going to be different. Now, worth noting here, just from our standpoint, that sort of backtracking a little bit, that if you look at our setup here, in most of the tests that we run, we usually have a listing of data, specifically quantitative data. If you look at what we have here, we do not have quantitative data anymore. So what would our data look like? Our data would be blue, blue, orange, green, yellow, green, orange, red, brown, brown, blue. You get the point, right? Dot, dot, dot. So our data is actually qualitative data. So worth noting that chi-square tests are major, basically their sole purpose is to measure qualitative data. So just take note, and this was mentioned earlier, I think. I just sort of skipped over it. But basically, the chi-square distribution's main focus is on qualitative data. So let's talk about sort of the logic of a goodness of fit test for chi-square. So you need to listen carefully here. This is very important. The better you understand the logic, the easier it's going to be just to do. So it says the logic of the chi-square test is to compare each observed frequency O of colors in the inspection of your current bag. So basically your O's are coming from counting your bag of 632 M&Ms, and you're comparing that to the expected frequency E of the Mars Inc. claim. So here's the problem. Right now, our expected frequencies aren't here, which means we're going to have to use these percentages to calculate them. Hopefully you already know how to do that based on our 632 number, but I'll show you in a second if that's not coming to you. Okay, it should make, right here, it says, it should make sense that the entire test will be based on how similar the overall observed frequencies are to the expected frequencies. As a whole, if the observed frequencies match up well with the expecteds, then we side with our null hypothesis that they're the same, and we do not reject it. If the observed frequencies do not match up with the expecteds, then we claim that they are different, and we would reject the null hypothesis. So clearly, what are we going to use to test that? We are going to use the chi-squared statistic with these O's and E's to figure that out. So just a note here, though, logically, what are the chances that the observed counts and the expected counts match up perfectly? Just like everything else in real life, very unlikely. So there's got to be a level of what matching up means. So how well do they match up in terms of determining whether it's going to warrant rejection or non-rejection of the null hypothesis? So let's get to the actual process for running a chi-square goodness of fit test. Okay, so suppose that you were given, you take your 632 M&Ms, you go on the kitchen table, and you spread them all out and you count them all. So what happens when you do that? You get this distribution of colored counts. So we call them the observed counts. So clearly, if you look at this, there are 6 colors, right? 6 colors. And each color has its own variable O. So believe it or not, these are the numbers that are going to be subbed into your chi-squared test statistic for the variable O. Okay, so this is sort of your observed part. So what about the expected part? So expected frequencies in a chi-squared goodness of fit test are calculated by the formula capital E equals N times P. N represents the sample size, the complete sample size, and P represents the relative frequency of the expected distribution. So, what are the, first of all, what is N? Well, the sample size is 632. So, if the sample size is 632, then that will be the N you use in every single scenario. What are the relative frequencies? P, the relative frequencies are the percentages claimed by Mars Inc. So what are we doing here? We're taking the value 632 and we're multiplying by these percentages to find the expected counts. And I would assume that most of you would know that already, but it is what it is, right? So hopefully you kind of know that logic, but that's what you get. So our first one is going to be N632 times P 0.24. So what are we going to get? Approximately 151.68. Then we're going to do our 632 again, but we're going to multiply by our second claim, which is 20%. We're going to continue to do that until we work all the way through the table and get the following values. I'm going to fill this out real quick. I'm not going to pause because it's there's only a few of them. Okay, so yes, the counts have decimals, and no, you're not really going to have 0.16 of an M&M. I'm sure you could figure that out with a slicer, but that's not the goal of this. The decimals are there for accuracy. So basically, we would have 151.68 expected blue M&Ms based on the Mars claim in this distribution. We would have 126.4 orange M&Ms based on this distribution. That is how you fill them out. So what are we doing essentially? We're basically looking at this and going, oh, we need to compare the observed and the expected frequency. So if you look at this real quick, look at these numbers compared to these numbers. Do they look somewhat consistent? Well, you might look and be like, oh, they're totally different. Well, I would say just by looking at them, they're not so different. I mean, you're seeing 150s, there's a 100 number, there's 90 and 100, 88, 61, 82 and 82, halfway between 92 and 6. So it's somewhat there. The whole idea of the test is going to be determined how close is it to determine the test itself. Just a note here, by the way, I just forgot to do this over here. So here I just said the first expected frequency is going to be 632 times 0.24, which is going to be 151.68. So you don't have to write that in. Basically, I just did it over here, right? But if you want to fill in the notes, you can. I just got ahead of myself a little bit there and went through all of the comparisons. So again, we need to compare these. So how do we compare them? We move on to our chi-square goodness of fit test. Specifically, the test statistic. Well, the test statistic is based on this formula right here. So our goal is to take that formula for each one of the colors. So we're going to do it 6 times for that formula. So again, here we go again. We have a nice table to fill in all the wonderfulness to make this work. So again, what could we do here? We could use the lists if we wanted to. So hypothetically, we could put O in L1, E in L2 for our, and by the way, these are just the numbers. I just copied this and this down. We need to find O minus E, which is in the denominator of this right here, or numerator, sorry, I misspoke. So we would do O minus E, which clearly would be L1 minus L2. If we did that, I'll fill these in quick. 3.32, 34.6, negative 11.12, negative 27.48, 9.84, negative 9.16. So then we could go, all right, well, what do I need? We need to do, so this is L3, by the way. We would need to do L4 is equal to L3 squared. So we would take all the values here in this column, and we would square them. So what would we get? We would get 11.0224. You notice I'm not rounding here because I want as accurate as possible. Okay, again, you can do this in the calculator if you want, just like we've been doing. You guys should be experts at this point with that. This makes life a lot easier. Okay, we get those values. Just a small tidbit here. Again, students will often ask, well, why do I have to, what's the point of squaring it? What does that do for me? Well, similar to when we were calculating some of the other earlier statistical formulas like standard deviation, if you just do O minus E, if you added all of these values here up, what are you going to get? You're actually, believe it or not, going to get approximately 0. So O minus E actually doesn't get you anything of relevance. So you have to square it and to generate something of relevance. So what do you get in that scenario? You get the values in that column. And then the last thing in this formula is that we divide by the expected counts. So the expected counts are in L2, so essentially you would do L5 is equal to L4 divided by L2. So when you do that, you're going to get a bunch of values, some small, some not so small, but you're going to get some values that are going to come together when you're done and add them all together to get the chi-square test statistic. So again, the formula is this. Note that we have the summation sign right here. So when we add it together, we're going to get 21.5011. So this is our chi-square test statistic. That is what we're going to use in order to run our test. And we're going to have to determine how far out that is based on our distribution that we run. But this is the process that you run through for each of these. And of course, we once again have our critical value and p-value approaches. We're going to have chi-squared. We're only in a right tail because we're dealing with a right skew distribution. One small thing that is totally different than anything you saw is the degrees of freedom. So degrees of freedom is equal to C minus 1. Note that C is the number of categories. So what are the categories in our problem? They are color. So we have 6 categories, so the degrees of freedom in this problem is going to be 5. So if you look down here, we're basically going to be doing the critical value approach to making this test, and then I'll also do the p-value so you know how to do both. Alright, so let's start basically with our process. So what do we have here? We have our alpha is 0.05, so our significance level is 0.05, which means we're looking for to find our critical value, we have to do chi-square sub 0.05 at a degrees of freedom, as we stated, 5. So how do we find that in our scenario? So we go to our chi-square table, right? Chi-square table is here. If you look across the top, our chi-squares are super big, so this actually has two sides to the table. So this ain't it, this one, because the subscripts are too big, so we move down to the second page. We have chi-square 0.05, which is right here, and we have 5 degrees of freedom. So we do our usual over, down, and over, and we're going to get 11.070 as our critical value. Okay, so what do? We put that on our graph here, 11.070, which is our chi-square value. Which means that anything in the tail is reject H0, anything in the remainder is do not reject H0, just like we've done in the F distribution before it when we were dealing with just tail values. Okay, so I'll fill in the blank here. It says you can clearly see that our chi-square statistic, so let's find that we did it, 21.5011. Okay, is to the what of our critical value 11.070? It is to the right of that. So over here somewhere is going to be our 21.5011. Okay, therefore we do what with H0? Well, it looks like we're in the rejection region, so we reject H0. Okay, so that's your decision basically. It's the same as what we've done before, no different. So what does that mean? So remember, let's go back to our null and alternative for our test. Get rid of the stuff that we had before. So our null and alternative was here. So our null stated that the M&M's colors were the same as Mars Inc., whereas the alternative said that they were different. Well, according to this, we are rejecting H0, so we are claiming that our bag of M&M's does not match Mars' claim for the color distribution of their M&Ms. Okay, so what about the p-value approach? Well, luckily, just like all the other distributions, there is a chi-squared CDF command in your calculator under distribution. So you would do second vars to get to the distribution menu, and you would see a little bit ways down the list. You would see that. So what are the commands in a chi-squared CDF? You would always do lower bounds to 1E99 because it goes on forever to the right with C-1 degrees of freedom. So what is our example? We would do chi-squared CDF. We would take our test statistics. So remember, this has nothing to do with CDF. That's just a cutoff. That's only used for the critical value test. Instead, we would take our test statistic. We would put it first. Then we would do 1E99 and then the 5 degrees of freedom for our test, and we would get a p-value of 0.0007, which is clearly less than alpha, which would lead to our rejection of our null hypothesis once again. So just like we've seen before, this is the same type of test that we run. Now, a small thing before we get going to the assumptions is in your calculator, this test is listed under your usual test location. It's called chi-squared GOF, as in goodness of fit test. Okay, so for your goodness of fit test, it's going to be a little bit complicated, only because you have to list your expecteds in L1 and L2. Not super complicated, obviously, because basically you would just have to make sure that this is actually in your calculator, run the test, and you would put them where they go. You would put the degrees of freedom in, and I'm going past where I was, and so these 3 things you need for observed and expected, and then you would just run the test, and you should get the same result that we're getting here. So very super simple. Okay, you might have remembered that at the beginning when I was listing out the test, I mentioned that I was going to do the assumptions at the end. Okay, why did I wait? Well, if you look at this entire process, you have to know what the assumptions are actually saying. So the first one says all expected frequencies are 1 or greater. So what you would do is you would go to your expected frequencies, which are right here, right? Your expected frequencies. And you would look at this and go, okay, our expected frequencies are greater than 1. The lowest one is 82, so that checks out fine for our test. You would also, there's another requirement, that at most 20% of the expected frequencies are less than 5. So basically you want to make sure that they should all be bigger than 5. That's what you want them to be. But if they aren't, then less than 20, at most 20% of them are less than 5. So if you look at, we don't have to worry about that because the entire distribution is greater than 5. So why is that important? Because how do you do a comparison between two distributions? If you expect one of the colors to be 0, wouldn't you just remove the color? I don't know if that makes sense to everybody, but it's logical, because what's the point of even having it in the test if you're expecting it to be 0? So you don't want that. It'll actually cause the test to have very inaccurate results if the expected counts are lower, or 0 or lower than 5 for any of them, for any of the ones that are there. But that's basically this if you want to read through it again. So it makes sense that we'll run through at least one example, we can do 2 here, of this goodness of fit test to make sure that everybody's clear on what you need to do. Okay, number 1, a researcher claims that the numbers of cups of coffee U.S. adults drink per day are distributed as shown in the figure. Okay, so they're looking at this figure right here. So it looks like we have 36% drink 0 cups, 26% 1 cup, and so forth around the pie chart. It says you randomly select 1,600 U.S. adults and ask them how many cups of coffee they drink per day. The table shows the results at alpha 0.01. Test the researcher's claim. Okay, so survey results are here. So basically, this is going to be where the expecteds come from, and this is going to be where the observed come from, right? So basically, this is where the logic of the test lies. So how do we start? Well, we can't check assumptions other than the random sample until we have our expected counts. So we have to do our calculations first. So null and alternative. So the null is going to be that the current distribution, our distribution, is the same as the claimed one. So actually, I'm going to have to use 2 lines here. So the distribution, in words, the distribution of cups of coffee is the same as the researcher's claim. We'll say claimed distribution, just so that we get that in there. Okay, but for all alternative hypotheses, since I just want to make sure that you're very clear on the null and it's correct. But for all alternatives, I'm basically just going to let you write the distributions are different. So you don't have to write out the same thing again with 1 word difference. That'll be fine. So this is your null and alternative. Okay, so after the null and alternative, what do we always concentrate on? We concentrate on our calculations, right? So what do we need? Well, we have our observed counts, so these are our O's, so we need our E's. So what do we need to do? We need to take our total U.S. adults, which is 1,600, and we have to multiply by each one of the percentages. So our first expected count is essentially 1,600 times 0.36. That is going to give us 576. Our next expected count, 1,600 times 0.26, which is going to give us 416. If we continue on with that strategy, we're going to get 304, 144, and 160 as our expected counts. Once we have our O and our E, we can then continue on with our table. So basically, we only have, it looks like, 5 categories here. So if we want, we can continue the table over on the left side over here. So we need our O minus E's, which we can put in our calculator. We need our O minus E squareds, and we need our O minus E squareds over E. Okay, so if you'd like to do, L1, L2, and then fill in the formulas like before, feel free to do that right now if you want to pause and go back and look and see how to do it again with the formulas from our example. So remember, I did these guys. So if you want to do that on your own and then see what the results are, that's fine, but I'm just going to write them out. You just got to pause the video. So O minus E is going to give us, our first one is 570 minus 576, which is negative 6. And then 432 minus 416, which is 16. And then we continue on with that and get these numbers. If we square those numbers, we get 36, 256, 44, 64, 16. And if we divide each one of those numbers by our E row, we are going to get a bunch of values that look like this. 0.065, 0.6154, 1.5921, 0.4 repeating, and 0.10. So the sum of this column is essentially going to be chi-square. Your chi-square test statistic, and if you add them all up, you get that. Now remember, in your calculator, if you get all of these, you can use the sum command and do sum of, I think it's going to be L5 or whatever it is when you're done. You could do that if you want, but generally this is what you're going to get for your chi-square. Once you have chi-square, you can go ahead and you can either choose to run your critical value test, or you can run your p-value. What I'm going to do basically is I'm going to do both. Because I want to make sure that you're all good with that. So let's just see if we don't, and by the way, that doesn't mean you do both. You don't need to do both. All I'm doing is making it better for you so that you understand the procedure. So if we run the critical value test, we're going to draw a obviously right skew distribution. We need to find the critical value. So what are we looking for? So we're looking for, in this test, alpha is 0.01. So we're looking for the chi-square sub 0.01 value at degrees of freedom equal to what? Well, it's always going to be categories. So there's 5 categories minus 1. So we're looking for basically 4 degrees of freedom. So we would go into our chi-square table, right? We would find our 0.01 column, and we would find our 4 degrees of freedom, and it looks like 13.277 is our value. 13.277. So this marks the cutoff between reject and do not reject. So what do? We would take our test statistic, find where it goes. It would go someplace over here, therefore we wouldn't reject H naught, so do not reject H naught. Okay, so we would go over here and say, if we don't reject H naught, that means the researcher's claim is accurate in terms of it's the same as the actual distribution that we came up with. So in that scenario, that's what we come up with. Now that's the critical value method. So what about the p-value method? So what would we do? We would use chi-square CDF, our calculator. We would take our test statistic, we want to find how much area there is to the right of it in a degrees of freedom chi-square curve of 4. If we do this value, we're going to get 0.5893, which is a gigantic p-value, not even close to near rejection. So again, it would lead us right back to do not reject H naught. So this is a typical chi-square goodness of fit test. It worked out pretty well. In terms of all the calculations. So my suggestion is when you're done with all this, you immediately go into your chi-square GOF test on your calculator, put in, make sure these are filled in L1 and L2 and degrees of freedom 4, and run it. And you should get the p-value there, you should get your test statistic. But what I wanted to point out, which some of you might find interesting, is when you run this test in the calculator, it actually gives you something else altogether. So what does that look like? So there is the very bottom value gives you, so it gives you chi-squared. Let me give you space here. So it gives you chi-squared, it gives you p-value, it gives you df. But then underneath that, it gives you CNTRB. Okay, so this is weird. Like, what is that? If you look at those numbers, what you're going to see when you, and by the way, you can hit the right button on the calculator to go to the right and see the entire thing. What you're going to find is those values are right here. So this O minus E squared over E calculation is the CNTRB values. So it's actually pretty neat. It gives you, in matrix form actually, it gives you all the values that that you would calculate at the end here to find chi-squared. Okay, so last problem. Since this is such a sort of an oddball type of thing, I figured I'd just do another one with you, just because we have some time here. So, or I have some time here. It says a doctor claims the number of births by day of the week is uniformly distributed. To test this claim, you randomly select 700 births from a recent year and record the day of the week in which each takes place. The table shows the results. At alpha 0.10, test the doctor's claim. Okay, so interesting concept here. So you're randomly selecting 700 births, or the doctor did, and you get this as your observed counts. But what is not included, nowhere do they say anything about E anywhere. So that's where the blue circle here comes in. When I say something is uniformly distributed, that means it's the same for each count. And if it's the same for each count, that means that you have to look at how many days there are. Clearly, there are 7 days a week. And you have to take your 700 births, do 700 divided by 7, and get each one, which is clearly going to be 100 for all 7 of them. So these are your expected counts, and this is hopefully extremely logical to you for each one of those expected number of births per day. So in that scenario, that's what it is. That's what we end up with. So let's go through some of the problem here. So what's the null going to be? The null is a statement of equality, meaning the distributions are the same. So you would say something like the distribution of births is the same throughout the days of the week. And the alternative would be the distributions. Distribution is different. Okay, as I said before, you can just write that if you like, and that's fine. So if we go through the process again, we have a little bit more space this time, so I'm going to put the tables over here. We're going to have O minus E here. We're going to have O minus E squared here. We'll have O minus E squared over E. Okay, remember this is L3, L4, L5. You use the proper formulas. So for example, the first one is going to be O minus E, 65 minus 100, which is negative 35. Next one is 107 minus 100, which is 7. And if we fill them all in as we go here for the 7 days of the week, we get this. If we square each one of those values in that column, we get the following. As our values, and if we take all of those and divide by our expected counts, we get 12.25 and so forth throughout the process. This is all stuff you can do on calculator. And our goal is to sum this entire column up and get 27.94. Okay, let's just do this. We'll do both methods again, just because why not? I have time here. So let's just make sure everybody is understanding what you're supposed to be doing. Make an obvious right skewed curve. We need a critical value. So we're trying, this is at alpha 0.10, so we're finding chi-squared of 0.10 at degrees of freedom equal to what? Well, there's 7 categories or days, so 6. We need to look in our chart for that, so we would go to this guy. Okay, eraser, where'd you go? There you are. So we would look up 6 degrees of freedom. We're now at 0.10. Be careful with that. Some people go to 0.01, and it looks like we're going to get 10.645. 10.645. Anything to the right, reject. Anything to the left, do not reject. So then we take our value, we go and it's someplace over on the right side of this, which means we clearly are going to reject H naught. So we're rejecting H naught. What does this mean? This means that clearly the number of births are different for the different days of the week in our scenario. So what about p-value, just to be clear? So if we did p-value instead for this, we're going to do chi-square CDF. We're going to take our 27.94 and find how much area there is in the tail to the right under 6 degrees of freedom, and that's going to give us approximately, for our standpoint, approximately 0. I think it's, I don't know, I think it's 5 or 4 zeros. Either way, it's approximately 0, so we are clearly going to reject H naught in this scenario. Okay, so what about assumptions? So are our expected counts all bigger than 1? They are. Are they all bigger than 5? Yes, so we don't have to worry about, ones that are lower than 5. So worth noting, by the way, as a side note, usually even though you got to go by what the book does, I tend to just tell students to make sure all are bigger than 5. If there's one that's not, then it's not a big deal, but if you start getting a bunch that are not bigger than 5, then that's an issue. So that's usually what I go by, but they also, by the way, did do random selection, so we're all good with assumptions, and this again is a good example of a goodness of fit test.